Here we have a coal burning power plant, burning coal at a rate of 4,000 tons per day. The ash content of the coal is 5%, the sulfur content is 1.5% by weight, both of them by weight. We're adding calcium carbonate in a limestone scrubbing system, and we want to capture 90% of the SO2 that's being generated. Well, this is a complicated problem now. There's a lot of things we need to do in this problem, and so let's take them one step at a time. First of all, you should always draw a diagram, and the tip right below here tells you that. Here we have the coal coming in to the furnace. We're going through some kind of a ESP or a baghouse or something that's going to collect, let's just put it in as an ESP, collect particulate matter. And then we go through some kind of a wet scrubber that's going to remove sulfur dioxide. And it's here in the wet scrubber that we're adding the calcium carbonate. We're collecting a sludge out the bottom that is primarily calcium sulfate and calcium sulfite. We're not too worried about that. We're simply wanting to calculate how much calcium carbonate we need to add. So, in looking at this problem, if we were to do a material balance around here, we've got SO2 coming into the scrubber and SO2 leaving the scrubber, calcium carbonate coming into the scrubber, and calcium sulfate and sulfite leaving the scrubber. We're capturing 90% of the SO2 that's generated. Let's put that in, 0.90% efficiency for capturing SO2 in the scrubber. Well, that begs the question, how much SO2 is being generated? And we can calculate that by material balance here, as we're bringing in air and burning the coal with oxygen, and any sulfur that's in the coal is going to react here in the furnace to form SO2. So the first step then, it occurs to me, the first step is we need to know how much sulfur we're bringing in that will be burned to SO2, because we know the ratio here, molecular weights of sulfur and oxygen and SO2. The SO2 that's formed is exactly twice as much as the sulfur that comes in. And the SO2 passes through the ESP, goes on to the scrubber. Okay, so for this question, question 16, we first do this chemical reaction that I just showed you and put down the atomic weights, molecular weights, to get this information down. We also know that the atomic weight of calcium carbonate is 100. 1 calcium, 1 carbon, and 3 oxygens. The reaction between SO2 and calcium carbonate is mole for mole, and therefore the mass ratio of calcium carbonate to SO2 is 100 to 64. All right, so the final answer then is 4,000 tons of coal per day times the mass fraction, 0.015 tons of sulfur for every ton of coal, times the molecular weight ratio of SO2 to sulfur. This gives us the tons of SO2, times 90% capture, gives us the amount of SO2 being captured, times the mass ratio of calcium carbonate to SO2 will give us the tonnage of calcium carbonate needed. Now, in practice, of course, you would want to give yourself a little bit more than the minimum required, because you want to maintain a good stoichiometric ratio. For more information on that, see the chapter on sulfur dioxide scrubbing. Question 17, very similar. We're following up on that other question. We've got the same coal-fired power plant burning coal at 4,000 tons per day, the same ash content, same sulfur content, but now we're going to be looking at the particulate matter. Previous problem, we were doing a material balance on sulfur, now we're doing a material balance on particulate matter. Assume 30% of the ash drops out in the furnace and 70% becomes fly ash. Calculate the efficiency required of a final control device to meet a PM emissions limit of 2 tons per day. Okay, go back to our diagram. Now we're talking about particulate matter, so here is the final control device, the ESP, or it could be a baghouse. It's going to be collecting that particulate matter. We're assuming no particulate matter collection occurs in the sulfur dioxide scrubber. That's conservative. You may get some particulate matter collected here, but you can't count on it, so you want to design the ESP to achieve the regulatory limit. All right, so how much particulate matter is coming in? Well, it comes in with the coal at 4,000 tons per day, and times 0.05 is the ash content coming in with that coal. In fact, let's look at this calculation as it's given here, typewritten. You won't have to look at my handwriting. The ash into the furnace is 4,000 tons per day of coal times 0.05 tons of ash per ton of coal, 200 tons per day. But some of that ash drops out in the furnace. Okay, we said right here, we've got some bottom ash coming from that furnace and some fly ash. So this would be the bottom ash, and up here is the fly ash. Fly ash coming out of the furnace is the 1 minus the bottom ash percentage, or 70% of 200 tons per day, or 140 tons per day. To meet an emissions regulatory limit of 2 tons per day, the efficiency required is the input to the ESP, which is the output from the furnace, minus the regulatory limit divided by the input, 98.6%. Okay, now let's look at problem 18. And here's a hint before you get started on problem 18. When calculating the temperature change of a gas that is being heated or cooled, or when estimating the heat to be added or removed to achieve the desired temperature change, you should use Appendix B in your text. Now let's look at Appendix B for a second here before we go on. In Appendix B, we have this table, B7, which are specific enthalpies of some gases. And air is one of the gases given, so that seems to be a little bit out of focus here. In any case, for a given temperature, you can read off the enthalpy of that gas. You could also use this chart for the enthalpy of air. A little bit less accurate, but perhaps a little bit quicker and easier to use. This chart shows the enthalpy in metric units versus the temperature in degrees C. That's what these little arrows mean. Use this axis and this axis together. Or in English units, you can use degrees Fahrenheit and BTUs per pound with the bottom curve. Okay, so now the problem is to calculate the amount of heat or the rate of heat addition needed to raise the temperature from 200 degrees F to 1400 degrees F if you're dealing with 4,000 actual cubic feet per minute at that temperature of 200. Again, we have the question of whether you'd be given data in standard cubic feet per minute or in actual cubic feet per minute. If it's actual cubic feet per minute, you need to know the temperature of the corresponding temperature. If they give you a question in standard cubic feet, it says the flow rate is so many standard cubic feet per minute, that always refers to the standard temperature, 77 degrees F, 25 degrees C. However, they might give you a really tricky wording and say you have so many standard cubic feet per minute, but it's entering at 200 degrees F. If they do that, the key is the standard cubic feet per minute. That is a certain temperature. It always refers back to standard temperature. So you know the mass by using the density of air at standard temperature. All right, let's see now how do we work this problem from 18. If we use the appendix, the table in the appendix, we can look up the enthalpy at 200 and the enthalpy at 1400 and get those two numbers. From another table in the appendix, we can get the density of air at 200. And we multiply the volumetric flow rate times the density to give us the mass flow rate of air times the difference in enthalpies is the amount of heat that's going to be required, 73,900 cubic feet per minute, BTUs per minute. Okay, let's move on to problem 19.